welcome to the first lecture of Chem 1. I am your professor, Mrs. Verissimo, and that is how you say my name, Verissimo. We are starting with Chapter 1. This is the first of 3 lectures on Chapter 1, and Chapter 1 covers matter, measurement, and problem solving. So today we're just going to start with kind of a general overview of what chemistry is and do a little bit of review on the phases of matter. So this is the general kind of aim of chemistry. Chemistry aims to discover everything possible about the characteristics of matter. And matter is anything that has mass and occupies space. And so there are these 4 different categories of the properties of matter that we can look at, or the characteristics of matter. So we can look at properties. This would be things like physical properties, like is it shiny, is it dull, or chemical properties, like does it react with water, and things like that. We can look at the structure of matter, how are those bonds being formed. We can look at the composition. So, what is the matter made out of? Is it made out of, hydrogen or oxygen? And then we'll spend a lot of time looking at the changes that occur with matter. And so these are things like, reactions. And obviously that's a large part of chemistry. So here's kind of an example. Chlorine gas, Cl2, is this deadly poisonous gas. It's green gas, and it was deployed on European battlefields in World War I. Sodium is this kind of soft silvery metal, and it's corrosive, and when you put it in water, it essentially explodes. It catches on fire. And so, we have a deadly poisonous gas, right? This green poisonous gas, and we have this silvery soft metal that explodes in water. And together, if you mix them up, then you will get table salt. You get stuff that we put on foods, right? And so this is just kind of demonstrating that the properties of these substances before a reaction are completely different than the properties after the reaction. So, why each of these substances has these general properties, right, is chemistry. And so that's what we're going to be studying in this class. How do reactions occur, and what do we get out of them? So, in general, science follows the scientific method, right? And so we're going to briefly cover it here. And you'll notice kind of Chapter 1 is kind of a random hodgepodge collection of science-y things, right? And so this is one of them. You've likely covered the scientific method in other classes before, so I'm just going to kind of briefly touch on it here. You can read more about it in your textbook, though, if you need more information. So the scientific method always starts with an observation. So like an example here, the color of my shirt is red, right? And we might go through and figure out, why is it red? Generally in chemistry, because things are happening on more of a smaller scale and, oftentimes in a lab, these observations won't be like the color of my shirt is red. It's more like, why did this reaction not proceed the way we thought it would? Or, why did it not make the product that we thought it would? But in general, an observation is describing or measuring an event. It could be in nature, it could be in a lab, right? But describing or observing an event. And then we will, make a hypothesis. Why do you think that, the reaction didn't happen the way it did? Or why, here, your example, the sweet taste of soda is due to the presence of sugar. Your hypothesis must be testable and falsifiable. So if you're not familiar with the word falsifiable, that means that somebody has to be able to prove you wrong, right? If there's nothing that anyone could do to prove your hypothesis wrong, then your hypothesis isn't any good, because then it would always be true no matter what. So it has to be testable, has to be falsifiable. And then you create an experiment to test your hypothesis. And then depending on the results of your experiment, you may come up with new questions, you may change your hypothesis, those are kind of, your options. It'll either be correct, you're like, wow, it was successful, and in which case you would likely do replicate experiments to make sure it wasn't just a fluke. But if it came out, that your hypothesis was incorrect, then you may change it, right, and see what happens. And out of this scientific method, we'll come up with 2 different things. You can come up with theories, or you can come up with scientific laws. And so theories and laws are kind of on the same level. A lot of times people think that theories, right, people will say, that's just a theory. It's not it's not, it might not be true. It's just an educated guess, right? Not true. That's a different use of the word theory. In scientific theory, it's a very well-established hypothesis. There's been, supported by considerable facts. Over time, you might modify it, you might refine it, right, as you get new information. But theories, the purpose of a theory is to provide a logical explanation as to why things happen the way they do. And so my example here is Einstein's general theory of relativity. It explains what gravity is, why gravity works the way it does. Okay, so it's not that, like we all take gravity as a fact, right? If you jump up, you will fall back down to the ground. Nobody's like you jump up and then you float to the ceiling. If you jump up, you go back to the ground. So Einstein's general theory of relativity, kind of on a simplistic matter, explains why this happens. So again, it's not really an educated guess. It has been, supported by considerable facts. Every time someone jumps up, they fall back to the ground. So that's a theory, a very well-established hypothesis that explains why things happen the way they do. Scientific law is a summary of observations, and so people often get these two things confused. Okay, so theories explain why things happen the way they do, and my best explanation for how to keep them straight with the laws is these laws are rules for how the natural world behaves under certain conditions. So after you take your theories, you might come up with scientific laws that say, okay, well, it always happens this way. And usually we can explain this through an equation, kind of like the law of conservation of energy. Energy must be created or destroyed. Energy cannot be created or destroyed. So if you lose energy from one place, that means it's being gained by somewhere else. And so we have equations that describe this process. So oftentimes with scientific laws, we'll have an equation, whereas theories are more of an explanation. And I hope that helps. Like I said, laws are not a higher stage than theories. Theories don't graduate and become laws. They're different. Theories explain why we observe what we do, and laws describe kind of what happens. I have posted a video on Canvas that explains more about theories versus laws. So you may want to check into that if you're still confused. Okay, more about matter that we were talking about earlier. Like I said, matter is defined as anything that occupies space and has mass. So essentially, matter is just stuff, everything. Everything is essentially matter. And even though matter may appear to be smooth and continuous, it's actually composed of lots of little tiny pieces that we call atoms or molecules, right? Depending on, if they're bonded or not. And sometimes we'll have compounds. But they're not, these smooth continuous surfaces. On a minute scale, right, a minuscule scale, we can see these individual atoms. So here on the right in the picture, we have an aluminum can, and those would be individual aluminum atoms that are making up that can. Obviously, they've been greatly magnified so that you can see them. So atoms are the teeny tiny particles that make up all matter. And in most substances, in general, we don't have just individual atoms, but instead we have them being joined up, and so they will form molecules, or they will form compounds. And usually we'll use the term molecules if we're talking about a covalently bonded substance, and we'll use the term compound more for ionically bonded substance. All right, solids, liquids, and gases. This, I would guess most people are familiar with, but we'll cover it anyways. So solids we have there on the left, right? If you were to put some solid, maybe a powder or something, in your Erlenmeyer, it would look kind of like that. We would have these closely packed individual particles. The liquid in that second picture, the particles are still very, very close together, but they have more fluidity. They're able to flow and move. They're not stuck in one place. And then a gas will go ahead and fill its entire container. As you can see, the gas particles are moving very quickly, and they are much farther apart. So we're going to do some specifics on each of those three types of matter. So solids, when you have a solid, the particles are packed very close together and they are fixed in position. So they're not going to move anywhere. So whenever you think about a solid, maybe think about, table salt, like we were talking about earlier, those salt crystals. And they're packed, like I said, very close together. and they are fixed in position, but they do vibrate in place. So these particles aren't just sitting there, they are moving. Anything that has a temperature above 0 Kelvin, which we'll get into more in the next lecture, but anything that has a temperature above 0 Kelvin is in fact moving. They just might be moving, very slowly or very, minusculely. So these solid particles are vibrating in place. And the close packing of these particles, right, the fact that they're really, really close together results in the solids being incompressible, right? You can't squish the solid any more than it already has been. You can't change the volume of the solid. So we have, a definite volume for these solids. And the inability of the particles to move around results in the solids retaining their shape and their volume when placed in a new container. So the particles also don't flow. So they have a definite shape and a definite volume. So when you think about these, they have definite shape and definite volume. We have two different types of solids. One of the types is a crystalline solid. So again, this would be like table salt, sodium chloride, right? These are solids that have their particles arranged in an orderly geometric pattern. So salt and diamonds. So here you can see they're alternating so that they can be packed as close together as they can be. Another type of solid is an amorphous solid, and these are solids that they don't have this regular pattern. They kind of are just mushed in there. And so this is what we have when we have plastic and we have glass. So two types of solids: crystalline, that alternating pattern, and then amorphous solids, which don't have a regular pattern. And these are going to be your best kind of examples of that. So liquids, particles in the liquid are also closely packed, but they have some ability to move around. So the particles of a liquid are moving faster than the particles of a solid. But they also have close packing, right? They're packed very close together. So they are also incompressible. So again, they have a definite volume, which is why we use things like graduated cylinders and Erlenmeyers to measure these liquids. However, they can flow. So the particles can take on the shape of whatever container you put them in. So if you pour them into an Erlenmeyer, or you pour them into a graduated cylinder, then they take on that shape. So they have a definite volume, but they don't have a definite shape. And then gases have much more energy than solids or liquids, right? So solids have very small amounts of energy, liquids have more energy, and gases have a lot of energy. And so because the gas particles have so much energy, they are able to completely break apart from each other and can fly about the container independently. So that's why you see these gas particles kind of flowing around doing their own thing. They have no definite shape, they have no definite volume. You will put in whatever container you put your gas in, they will take up all of the space, fill the entire container. So I like to say this is why, if somebody brings, say rotten eggs into the lab or into the classroom, then you'll be able to smell them, right? Because over time, those particles will aerosolize and will spread and fill the entire room. So also, in the gas state, there's a lot of empty space between these particles. So gases are compressible because, right, you can squish all those particles closer together. So this is why we have things like, CO2 cylinders, like if you're, going to go paintballing or whatever, you will have compressed carbon dioxide. So those gas particles have been squished closer and closer together under high pressure, so that you can, hold a lot more gas particles in a given container. So, like I said, there's a lot of empty space. Gas particles can be compressed. So this over here, this is an oxygen tank on a diver. And because these particles are not held in close contact, they're moving freely. The gases can expand and they will fill and take the shape of whatever container. And they also, and this is different, they will flow. People often don't think of gases as flowing, right? But they do. You can technically pour a gas. You don't think of it as, you might think of pouring a liquid, but you can. So here's a summary: solids, liquids, and gases. So solids, they're very rigid. They have a fixed shape and a fixed volume. They cannot be squashed, right? You cannot compress them. Liquids are not rigid, right? They can kind of shift around. They do not have a fixed shape, but they do have a fixed volume, which is why we can measure their volumes. And again, can't be squashed, right? You can't compress them. Gases, though, not rigid, no fixed shape, no fixed volume, and you can compress them into a smaller container. And so this is the end of our first lecture on Chapter 1. So I will see you all next time.